Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will learn about the transistor transistor logic, which is also commonly known as the TTL. So the logic gates which we have seen so far are designed using the different IC technologies, which is also known as the logic families. So the common logic families which are typically used in the IC fabrication are RTL, DTL, TTL, ECL and the CMOS. So these logic families or the IC technology which is used in designing these logic gates determines their characteristics like the speed, voltage levels, fan out and the power consumption. So some of the logic families like the RTL and the DTL are nowadays obsolete, but the other logic families like the TTL, ECL and the CMOS are still in the used. So in the earlier videos, we have already seen the CMOS logic. So similarly, in this video, we will learn about the TTL logic. So as its name suggests, this TTL logic is based on the bipolar junction transistor. So every logic family has a defined range of input and output voltages that can be considered as either logic high or the logic low. So in case of the TTL logic, any input voltage between 0 to 0.8 volt can be considered as the logic 0, while any input voltage between 2 volt to 5 volt can be considered as the logic 1. Similarly for the output, any output voltage between the 2.4 volt to 5 volt will be considered as the logic high, while any output voltage between 0 to zero point 0.4 volt will be considered as the logic low. So now, let us see the circuit of the TTL logic gate. So this is the internal circuit of the TTL inverter. So in this video, what we will do, we will understand the working of this TTL logic gate with the help of this inverter circuit, and in the next video, we will see that how to design the other TTL logic gates like the NAND gate, NOR gate and the other logic gates. So if you see the voltage transfer characteristic of this TTL inverter, then this is how it will look like. So this voltage transfer characteristic basically shows as the input changes, then how the output voltage changes. So in digital circuits, these logic gates are used in these two regions. So when the input is low, then the output is high and it will be more than 3.6 volt. And similarly, when the input is more than 2 volt, then the output is typically around 0.2 volt. And this can be considered as the logic low. So to understand how this TTL circuit works, first we should understand the different stages of the TTL circuit. So in this TTL circuit, the first stage is known as the current steering part. So basically, this part directs the current either towards the input side or towards the base of the transistor Q2 depending on the input voltage. Then if you see the next part, then that is known as the phase splitter. So basically, this part generates the two output voltages which are complement of the each other. That means whenever the one output is increasing at that time, the other output is reducing. For example, when the input voltage is increased from the low to high, at that time the voltage at the collector of the Q2 starts reducing, and at the same time the voltage at the emitter of this Q2 will increase. And these two outputs drives the final stage of the TTL circuit, that is known as the totem pole, because here the two transistors Q3 and Q4 are stacked on the each other like the totem pole. So here, since they are fed through the phase splitter outputs, so at any given time only one of the transistor will be on. So it will get clear to you when we see the working of the TTL circuit. So first, let us see how the circuit will work whenever the input is low. So let's say this input is equal to 0.2 volt, because we have just seen that for the TTL logic, when the input is between 0 to 0.8 volt, then it can be considered as the logic 0. So for this input, let us see how this circuit will behave. So here, I am assuming that you are already aware about the basics of the BJT, and in case if you are not aware, then please go through the basics of the BJT, or for that you can watch this playlist. Alright, so now when the input is 0.2 volt, then this base emitter junction of the Q1 will become forward biased, because here the voltage applied to the base is equal to VCC or the 5 volt, While if we see the voltage at the emitter, then that is equal to 0.2 volt. That means here, the base emitter junction of the Q1 will become forward biased. That means now, if we see the voltage at the base, then that would be equal to zero point 0.2 plus 0.7 volt, or roughly it is equal to 0.9 volt. So now, if we see the collector base junction of the Q1, then it will be also forward biased, because here this transistor is the NPN transistor, and here the voltage at this node will be close to 0 volt. So here, for this transistor Q1, both base emitter junction and the collector base junction will get forward biased, and therefore this Q1 will operate in the saturation. So here, since this Q1 is operating in the saturation region, so the small amount of current is going away from the base of the Q2. Moreover, the base of the Q2 does not have sufficient voltage to turn on this transistor Q2, and therefore in this condition only small amount of current will flow in this direction, and through this 4 kilo ohm resistor the majority of the current will flow in this direction. That means in this condition the Q2 will be off, and since the Q2 is off, so the drop across this resistor R3 will also be equal to 0, and therefore the base of the Q4 will not have sufficient voltage to turn it on, and therefore this transistor Q4 will also remain in the off condition. So in this condition, since the Q2 and Q4 are off, so the voltage at this node will be close to VCC. So here, this is the output node, and through the load it is connected to the ground terminal. So here, to forward bias this base emitter junction of the transistor Q3, the voltage at this node should be equal to the VBE of the Q3 plus the drop across the diode. That means it should be roughly equal to 1.4 volt. And here, since it is more than that, so the base emitter junction of the Q3 will get forward biased. That means in this condition, the Q3 will be in the on condition, and through this path the current will flow in the base of the Q3, and if we see the voltage at the output node, then that is roughly equal to 3.6 volt. That means the VB minus the drop across the base emitter junction minus the drop across the diode. But here let us determine whether the collector base junction of the Q3 is forward biased or the reverse biased. So if it is reverse biased, then the Q3 will operate in the active region, and if it is forward biased, then the Q3 will operate in the saturation. So for this collector base junction to be forward biased, the voltage at the collector should be at least 0.6 to 0.7 volt less than the base voltage, right? So here if you see, then the base voltage is close to VCC. So we can say that that is roughly equal to 5 volt. That means here the voltage at the collector should be around 4.2 to 4.3 volt. So if that is the case, then this base collector junction is forward biased, otherwise it is reverse biased. So here the drop across the diode is roughly around 0.7 volt. That means here if we see the voltage at this node, then that is equal to 3.6 plus 0.7 volt, that is equal to 4.3 volt. That means here the voltage at the emitter of this transistor Q3 is roughly equal to 4.3 volt. Moreover, here if we assume that this Q3 is operating in the saturation, in that condition also the minimum voltage drop across the VCE will be equal to 0.2 volt. So in that case, if we see the voltage at the collector, then that would be equal to this 4.3 volt plus 0.2 volt, that is equal to 4.5 volt. So if that is the case, then the difference in voltage between the base and the collector would be less than 0.7 volt, and due to that this base collector junction will not get forward biased, because here the voltage difference between the base and the collector is not able to cross the 0.6 to 0.7 volt. So we can say that here this collector base junction is operating in the reverse bias condition, and therefore we can say that here this transistor Q3 is operating in the active region. So we can say that when the input voltage is low, then the output voltage is around 3.6 volt. And as we have seen, it can be considered as the logic high. So in this way, when the input to this TTL inverter is low, then its output will be high. So we can say that in this voltage transfer characteristic, in this region, when the input is low, at that time, this Q1 is in the saturation, while the Q2 and Q4 will remain in the off condition. And similarly, if we see the transistor Q3, then it will be on and it will operate in the active region. So similarly, let us see how this inverter circuit works when the input is high. So let's say the input to the inverter is equal to 3.6 volt, because this input voltage can be considered as the logic high, right? So when the input is 3.6 volt, then the same will also appear at the emitter of the transistor Q1. Now here, through this resistor R1, this 5 volt is connected to the base of the Q1. But here, the voltage at the base will not go beyond the 2.1 volt. So let us see why. So here initially, let us assume that this base emitter junction gets forward biased, and due to that, the voltage at this node is equal to 3.6 volt plus 0.7 volt, that is roughly equal to 4.3 volt. And due to that, this collector base junction will also get forward biased. So in that case, the voltage at this node will be equal to 4.3 minus 0.6 volt, that is roughly equal to 3.7 volt. So here, if the voltage at the base of the Q2 is equal to 3.7 volt, then the base emitter junction of the Q2 will also get forward biased. And if we see the voltage over here or at the emitter of the transistor Q2, then that is roughly equal to 3 volt. So this voltage will also appear directly between the base emitter of the Q4. That means here, the base emitter junction of the Q4 will also get forward biased. And if that is the case, then the voltage between these two nodes will not be more than the 0.7 or the 0.75 volts, right? So due to that, what will happen? This Q4 will be in the on condition and it will operate in the saturation. And if we see the voltage at the VB of the Q4, then that will be around 0.75 volt. Similarly, this Q2 will also operate in the saturation, and therefore the VBE of the Q2 will also be around 0.75 volt. That means if we see the voltage at the base of the Q2, then that is roughly equal to 1.5 volt. And since the collector base junction of the Q1 is forward biased, so the voltage at the base of the Q1 will be roughly equal to this 1.5 volt plus 0.6 volt, that is roughly equal to 2.1 volt. That means here, if this Q2 and Q4 is in the on condition and they are operating in the saturation, then the voltage at the base of the Q1 will not go beyond the 2.1 volt. Because as you know, when the transistor is in the on condition, then its base emitter voltage cannot go beyond the 0.7 or the 0.75 volt. That means here, the base of the Q1 will not go beyond the 2.1 volt. And therefore, when this input is high, then this base emitter junction of the Q1 will get reverse biased. So typically, when the transistor is operating in the active region, at that time, this base emitter junction is forward biased and the collector base junction is reverse biased. But here, it is exactly opposite to that. That means here, the Q1 will operate in the reverse active region. And due to that, through this R1, the current will flow into the base of the Q2 instead of going in the other direction. So now, the Q2 and Q4 will operate in the saturation, and because of that, the large amount of current will flow into the collector of the Q2. So due to this flow of current, the voltage drop across the R2 will be more. And due to that, now the voltage at the base of the Q3 will be less, and it will not be enough to turn on this Q3. So let us approximately find out what is the voltage at the base of the Q3. So here, the emitter current of the Q2 will get divided in the two parts. So some current will flow through this resistor, while the remaining current will flow into the base of the Q4. And here, the drop across this 1K resistor would be around 0.75 volt. And here, since the Q4 is operating in the saturation, so this voltage VCE or the output will be roughly around 0.2 volt. Similarly, since the Q2 is also operating in the saturation, so this voltage VCE will also be roughly around 0.25 volt. And therefore, if we see the voltage at this node, then that is roughly equal to 1 volt. So this voltage will not be sufficient to turn on this transistor Q3, because here if the output is 0.2 volt, then to turn on this transistor Q3 we will require this 0.2 volt plus the drop across this diode, that is 0.7 volt, plus the drop across the VB, that is one more 0.7 volt. So we can say that to turn on this transistor Q3 we will roughly require this 0.2 volt plus 1.4 volt, that is roughly equal to 1.6 volt. That means here the Q3 will remain in the off condition. And in this way, when the input to the TTL inverter is high, then the output will be low and it will be close to 0.2 volt. So here in this transfer characteristic if we see, then during this region of operation, the Q1 will operate in the reverse active region while the Q2 and Q4 will operate in the saturation. Here if we see the transistor Q3, then it will remain in the off condition. So that is how this circuit works as the TTL inverter. That means when the input is low, then the output is high, and when the input is high, then the output is low. But now let us also see when the input is between this range, then how the output changes. So as you can see, up to certain input voltage, this output almost remains constant up to 3.6 volt. So basically, it will remain constant until this Q2 gets turned on. So for that, first of all let us see when this Q2 will get turned on. So here, this Q2 will be in the on condition when the voltage at the base of the Q2 is more than 0.7 volt. So it will happen when the input is more than 0.6 volt. So let's say the input is equal to 0.7 volt. So when it is 0.7 volt, then the base of the Q1 will be at the 1.4 volt, right? And if we see the voltage at the collector, then that is roughly equal to 0.8 volt. Because here, when the input is around 0.7 volt, at that time, this base emitter junction gets forward biased, and due to that, the voltage at the base will be roughly around 1.4 volt. And similarly, since the collector base junction is also get forward biased, so the voltage at the collector or the voltage at the base of the Q2 will be roughly around 0.8 volt. That means once again, here this Q1 is operating in the saturation, because here both base emitter junction and the collector base junctions are forward biased. And since it is operating in the saturation, so the drop between the collector and the emitter would be roughly around 0.1 to 0.2 volt. So we can say that when the voltage at the input is more than 0.6 volt, then the voltage at the base of the Q2 will be slightly more than 0.7 volt. And due to that, this base emitter junction of the Q2 will get forward biased. So as it gets forward biased, then the current will start flowing through the base of the Q2. So earlier if you see, then when the input was less than 0.6 volt, at that time, the majority of the current was flowing into the input side via this R1. But now, some of the current will get diverted towards the base of the Q2. And since the current starts flowing through the base of the Q2, so due to that, we will also get some emitter current. And because of that, the voltage will start getting built up across this resistor R3. But until the voltage drop across the R3 is not more than 0.7 volt, this Q4 will remain in the off condition. So here, since there is some flow of current through the collector of the Q2, so due to that, there will be a more voltage drop across the R2. And because of that, the voltage at the base of the Q3 will reduce. And effectively, the output voltage will also reduce. Because we know that this Vout is equal to this VB minus 1.4 volt. So as the VB reduces, then the output voltage will also reduce. So we can say that when the input voltage is more than 0.6 volt, at that time, this Q2 and Q3 will be in the on condition, while the Q4 will be in the off condition. That means in this region of operation, the Q1 is operating in the saturation, while the Q2 and Q3 will operate in the active region. And if we see the Q4, then it will remain in the off condition. So until this Q4 is off, this output voltage will reduce at the fixed rate with the increase in the input voltage. But once the Q4 gets turned on, this output voltage will reduce even at the faster rate. So first, let us see when this Q4 will get turned on, and once it is turned on, then how the output voltage will fall sharply. So here, this Q4 will get turned on when the voltage across the R3 is more than 0.6 volt. So as soon as this voltage reaches the 0.65 volt, then the base emitter junction of the Q4 will get forward biased. And for that to happen, let us find out the required input voltage. So let's say the voltage across the base emitter junction of the Q4 is equal to 0.65 volt. And let's say across this transistor Q2, the voltage is also equal to 0.65 volt. That means if we see the voltage at the base of the Q2, then that is equal to roughly 1.3 volt. And here, if we subtract the drop across the transistor Q1, then the input voltage should be more than 1.2 volt. Because here, the Q1 is operating in the saturation right now. So we can say that when the input is more than 1.2 volt, at that time, this Q4 will get turned on. And now, it will also start drawing the current through the emitter of the Q2. That means effectively, now the emitter current of the Q2 will increase. So further, if we increase this input voltage, then effectively, the voltage which is appearing at the base of the Q2 will increase. And due to that, the base current as well as the collector current of the Q2 will increase. And due to that, now the drop across the resistor R2 will further increase. And due to that drop, now the voltage which is appearing at the base of the Q3 will further reduce. Or effectively we can say that now the output voltage will fall more sharply. So due to that, here we are seeing the sharp fall. And after the certain increase in the voltage drop across the resistor R2, the voltage at the base of the Q3 will not be sufficient to keep the transistor Q3 in the on condition. And due to that, now the Q3 will also go in the off state. So we can say that during this region of operation, the Q1 will still operate in the saturation while the Q2 will operate in the active region. Moreover, the Q4 will also get turned on, and as soon as it gets turned on, then the Q3 will go from the on to off state. So now, during this region of operation, with the further little increase in the input voltage, the voltage at the base of the Q2 will increase, and due to that, the emitter current of the Q2 will further increase. And since the part of the emitter current is directly going into the base of the Q4, so first, this Q4 will go into the saturation. And as it goes into the saturation, then the output voltage will further reduce and it will be close to 0.2 volt. So we can say that when the input is more than 1.45 volt, then assuming this base emitter junction is forward biased, the voltage at the base of the Q1 will be roughly equal to 2.15 volt. And here, since the collector base junction is also forward biased, so the voltage over here will be roughly equal to 1.5 volt. So around at this voltage, this collector base junction of the Q2 will also get forward biased, and now this Q2 will also operate in the saturation. So now around at this voltage, both Q2 and Q4 are operating in the saturation, and in this condition, the Q3 will go in the off state. And here, now the output voltage is close to 0.2 volt. So now, if we further increase the input voltage, then as we have seen, the voltage at the base of the Q1 will not go beyond the 2.15 volt. So we can say that the voltage at the base of the Q1 is restricted to around 2.1 to 2.15 volt. So when the input voltage goes above this 1.5 volt, at that time, this base emitter junction of the Q1 will get reverse biased. That means whenever the input is more than this, then this base emitter junction of the Q1 will get reversed biased, and at the same time, this collector base junction will get forward biased. So in this condition, this Q1 will operate in the reverse active region. So that is the case when we consider the input as the high. So we have seen that in this region of operation, the Q1 is operating in the reverse active region, while the Q2 and Q4 are operating in the saturation region. And at the same time, this Q3 remains in the off condition. So that is the voltage transfer characteristic of the TTL inverter. And keeping these voltages in mind, the upper and lower limits of the TTL inputs and the outputs are defined. So for this TTL logic, this VIL is equal to 0.8 volt. That is the maximum input voltage that can be considered as the logic 0. Similarly, if we see the VOL, then that is equal to zero point 0.4 volt. That is the maximum output voltage that can be considered as the logic 0. So as per this voltage transfer characteristic, when the input is between 0 to 0.8 volt, at that time, the output is always more than the 3 volt. That means whenever the input is between 0 to 0.8 volt, at that time, we will surely get the desired result. But here, conservatively, this range is kept from 2.4 volt to 5 volt because during the fabrication, the values of the resistor as well as the characteristic of this transistor might differ slightly from batch to batch. So keeping that tolerance in mind, these input and output voltage ranges are defined. So for the TTL logic, if we see the low state noise margin, then that is equal to 0.4 volt. Because here the VIL is equal to 0.8 volt while the VOL is equal to 0.4 volt. That means the low state noise margin is equal to 0.4 volt. Well, what is noise margin? I have already covered earlier in the separate video. So here I am not going in the detail, but for more info you can check that video. Similarly, if you see the high state, then here this VIH is equal to 2 volt. So this VIH is the minimum input voltage that can be considered as the logic high. And similarly, this VOH is equal to 2.4 volt. That is the minimum output voltage that can be considered as the logic high. So as per this voltage transfer characteristic, when the input is equal to 2 volt, at that time, the output is around 0.2 volt. Or we can say that is equal to logic 0. That means whenever the input is equal to VIH, at that time also, the circuit will work properly. And here if you observe, then even at the 1.5 volt also, we are getting the logic 0. But considering all tolerances, this TTL range is kept more conservatively. So now, if we see the high state noise margin, then that is equal to VOH minus VIH. So here, this VOH is equal to 2.4 volt. And similarly, if we see the VIH, then that is equal to 2 volt. That means for this TTL logic, this high state noise margin is also equal to 0.4 volt. So we can say that for this TTL logic, both high state and the low state noise margin is equal to 0.4 volt. So similarly, now let us see the fan out for this TTL logic circuit. So as we have seen, the fan out defines the maximum number of other logic gates that can be connected at the output of the logic gate. So for the TTL logic family, these are the maximum allowed values of the input and the output currents. So when the output of the logic gate is low, then the logic gate sinks the current, and when the output is high, then it will source the current. So here, when the output is low, then the logic gate will sink the current from the other logic gates. And at that time, the other logic gates will source that current. So this IIL is the maximum current that can flow out of the logic gate when its input is low. For example, if we consider this inverter, then for this inverter, when the input is low, let's say a 0.2 volt, at that time, the voltage at the base will be roughly around 0.9 volt. And the current that is flowing in this direction will be roughly equal to this 4 volt divided by 4 kilo ohm. That is equal to 1 milliampere. So the maximum value that can flow in this direction is defined as the 1.6 milliampere. Similarly, this IOL is equal to 16 milliampere. So this IOL is the maximum current that the logic gate can sink when its output is low. So as I said, when the output of the logic gate is low, then it will sink the current from the other logic gates. So here, the maximum allowed value of this current is equal to 16 milliampere. That means here, this output can sink maximum up to 16 milliampere of current. And we have seen that each logic gate can supply maximum up to 1.6 milliampere of current. So from this we can say that the low state fan out for these TTL circuits is equal to IOL divided by IIL. So here the IOL is equal to 16 milliampere while the IIL is equal to 1.6 milliampere, and therefore the low state fan out is equal to 10. That means whenever the input of the logic gate is low, at that time maximum we can connect up to 10 loads. So similarly, let us see the high state fan out. So for that we need to see the IOH and the IIL. So this IOH is the maximum current that the logic gate can source when its output is high. So for example, when this output is high, then it will supply the current, and this current will flow through the other logic gates. That means the other logic gates which are connected at the output of this logic gate will sink that current. So for the input side, the maximum current limit is defined as the IIH, that is equal to 40 microampere. That is the maximum current that the TTL logic gate can sink when the input is high. So here this IIH is equal to 40 microampere, and here the value of the IOH is equal to 400 microampere. So this IOH is the maximum current that can be supplied by the logic gate when its output is high. So we can say that this high state fan out is equal to IOH divided by IIH. So here the IOH is equal to 400 microampere while the IIH is equal to 40 microampere. That means the high state fan out is also equal to 10. So we can say that for the TTL logic, when the output is high, then at the most we can connect the 10 output loads. And of course, this is valid when the connected logic gates are also of the TTL logic family. But suppose if we are connecting the other type of logic family at the output, then once again we need to check all these values for the other logic family. And according to those values, we can decide how many logic gates that we can connect at the output side. But for this TTL logic gates, the value of this high state and the low state fan out is equal to 10. So if we connect more than these logic gates at the output, then the performance of the logic gate is not guaranteed. So that is the noise margin and the fan out of the TTL gates. So I hope in this video you understood how this TTL circuit works and what is the voltage transfer characteristic of the TTL inverter. And moreover, I hope you also understood how the noise margin and the fan out can be calculated for the TTL circuits. So once we understood the working of the basic TTL inverter, so similarly in the next video, we will see the circuits of the other TTL logic gates like the NOR gate, NAND gate and the other logic gates. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.